So thank you for emailing in your questions for the virtual office hours today. It's January 26th. First, I have a couple of announcements that I can email out as well, that lab grades are posted in D2L and exam grades will be posted in D2L as well when they are ready after our midterm this Saturday. Also, quiz and homework grades are posted in Calc Portal. The reason why these are maintained separately is because they need to end, and I want to minimize errors by crossing between the two. If you have questions about your grade or if you'd like help calculating your grade, send me an email and I'm happy to do that. The questions that we have for office hours are types of indeterminate forms, rules for limits at infinity, and also an example of a tricky trig limit. So for that first question, I went ahead and added a video to section 2.5 so that it'll be a little bit more clear for people. But really there are just 4 different types of indeterminate forms, and of these 4 types, really we end up with focusing mostly on the first 2, particularly in this class, although you can look at some of these other ones if you're working in different classes. So the first type is a 0 divided by 0 indeterminate form, and I worked through an example of that in the video. Infinity divided by infinity, or similarly negative infinity divided by negative infinity. Really the negatives would cancel in that case. Or a negative infinity and an infinity, those are all indeterminate forms. It's because we don't know what the size of infinity is for these answers. So again, go check out that video at section 2.5 and I'll give you a lot more detail for those types of questions. Another question that we had was some more examples for algebraically evaluating rules for limits at infinity. And I summarized these rules in a set of 3 different bullet points. The first is, if the degree of the numerator is higher than the degree of the denominator, we know that the limit is going to be infinite. And so this is something that sort of makes sense intuitively. When looking at this limit, this x to the 5th is going to be a much more powerful term than these subsequent terms. These subsequent terms are sort of pocket change, and I see that this leading coefficient, or this leading term to infinity, and nothing in the denominator is going to get big enough to cancel it out. The way that we formally evaluate this algebraically is I'm going to divide out this largest degree term. So I'm going to look at what happens when I multiply the numerator by 1 over x to the 5th and the denominator by 1 over x to the 5th. And I'm doing that because I notice that this is the limit as x goes to infinity. By the distributive property, I end up with 2 minus x to the 3rd divided by x to the 5th is 1 over x squared. And x to the 3rd divided by x to the 5th, I'm going to end up with 4 divided by x squared. And look what happens when I evaluate this limit. When x goes to infinity, what happens to each of these pieces? By one of the theorems that we talked about, we see that when we take this limit, maybe I'll just take the limit and I'll say that this approaches 2 minus 1 over infinity, and this is notation, so I'll put this in a little thought cloud. 4 divided by infinity. I'm not writing equals because infinity isn't a number. We can't actually plug that in as a value. But what you're thinking to yourself is, you know that this limit, as x goes to infinity, this becomes 1 divided by infinity, which is 0. This also becomes 4 divided by infinity, which is 0. And I end up with this infinite result. I end up with 2 divided by 0, which is an infinite result. Your calculator will say that it's undefined, and really what's happening is this denominator is getting smaller and smaller and smaller. So when I divide by a smaller and smaller number, the result is going to get bigger and bigger and bigger, which is infinite. So that's one of the rules. The next rule is maybe I'll move this down. If the degree of the denominator is higher than the degree of the numerator, the limit is 0. And we'll look at a similar example So again, just looking at it in terms of a qualitative analysis, I see that none of the terms on top are anywhere near as big as what happens when I take x to the 8th. Even multiplying x to the 8th times 3, that's going to be way bigger than taking x to the 5th times 4 as my x values approach infinity. So formally, I'm going to get rid of this x to the 8th term by multiplying the numerator and the denominator by 1 over x to the 8th. And so algebraically, we're left with x approaches infinity of this becomes 4 over x cubed minus 1 over, right, because I have a squared on top and an eighth, it becomes 8x to the 6th plus 1 over x to the 8th, all divided by 3 minus 2 divided by x to the 8th. And again, we see what happens when I take this limit to infinity. All of these little pieces are going to go to 0. I end up with 0 minus 0 plus 0 in the numerator, and I get 3 minus 0 on the bottom, which is just 3. And so this limit is 0 thirds, and if I don't have any thirds, that's the same thing as 0. Finally, we have the case where the degrees of the numerator and denominator are equal. And so we're going to be left with the ratio of leading coefficients as the limit. Algebraically, we can see this. Again, we're saying, oh, these backcases don't really matter as my limit goes to infinity, and it means that I'm left with 5x by 10x cubed, and I can divide those out, and I'm left with 5/10. That's my qualitative analysis. Formally, we'll multiply both the numerator and the denominator by 1 over the largest x to the degree power, and I am left with the limit as x approaches infinity of 5 minus 2 over x plus 1 over x cubed in the numerator by the distributive property again. And then I'm going to distribute the denominator, and I end up with 10 plus 1 over x squared plus 4 over x cubed. So evaluating this limit, we know that as x approaches infinity, all of these pieces will go to 0. 2 divided by a really big number goes to 0, and I'm left with 5 minus 0 plus 0 divided by 10 plus 0 plus 0, or 5/10, which is 1/2. Which notice was just the ratio of the way is that when comparing these, you can always look at the ratio of leading coefficients. It's just in this previous case, the leading coefficient when matching it up was like 0x plus this, and notice that 0 over 3. Finally, I was asked about how you can use intermediate value theorem. An intermediate value theorem, actually our applications are usually really pretty simplistic, but it only works for continuous functions. And there are times that maybe algebraically you're presented with a function that's not continuous, and it means that your function might not take on every value in between if there were gaps or holes in your original function, right? That on this closed interval from A to B, I see that because this original function wasn't continuous, I'm not going to hit every possible y value. Y values in this range are not going to be used. That said, for this course in particular, I think it's important to understand that the intermediate value theorem exists, but we aren't going to work with it algebraically other than to verify some results that, at least from our perspective, are probably trivial results. Finally, let's take a look at this example. This is a very classic type of problem, and we're going to take advantage of Theorem 2. Theorem 2 in this section, I should label this section, is limits of trig functions, which I think is 2.7. 2.7, and this is just a generic problem pulled out of that section. Theorem 2 tells us that the limit as x approaches 0 of sine x divided by x is equal to 1. And the best way to verify that is either using L'Hopital's rule, which we'll see at the end of the term, or using the squeeze theorem. But notice we can't directly apply this theorem yet, because the way that this function is written, that I have 4t up in here, and I have just a single t down in the bottom, that here my x's match, here my t's don't. So I'm going to multiply by 1. I'm going to multiply the numerator and the denominator by 4. That means that I can rewrite this as the limit as t approaches 0 of 4 sine of 4t divided by 4t. The reason why I'm doing that is because now it's more clear that I can apply this theorem to this section of the product. And for clarity's sake, I can even rewrite this because of our limit laws, because this is multiplication. I can even write this as 4 times the limit as t approaches 0 of sine of 4t divided by 4t. Limit laws, I'm pulling out this factor out front. Now, this is where the trick comes in. X equal to 4t. Well, why am I allowed to do this? Because I see that if I turn these 4t's into an x, it becomes what I want. I have to be careful about the fact that as t approaches 0, we also have to check that that means that x would approach 0. And in this case, it's true. So I'm going to just say note, as t approaches 0, that also means that 4t would approach 0. So we can apply Theorem 2. And I'm going to rewrite this equation up here in terms of x's. So I'm going to rewrite this, that this limit up here is exactly equal to 4 times the limit as x approaches 0 of sine of x divided by x. And by Theorem 2, we know that this limit is equal to 1, so we get 4 times 1, which is equal to 4. Thank you for your questions, and please let me know if you have future questions as well.